Hello, everyone. Just a couple of minutes for me to prepare, and we'll start our webinar.
Hello.
Oh, hi, Vlad. You're here.
Yes. Okay. So welcome everyone. Sorry, I don't have my camera. Well, I do, but Vlada is going to do the webinar today. Vlada is the author of some of our assignments, so please welcome. And let me just make you host. All right, so you should be host now.
Yeah, okay. Let's see if I can share. Yeah, I can. Okay.
Perfect.
So let me just...
So we're expecting about 15 to 20 people, but this is recorded, so this will be published, and quite a few more people will watch it later.
Yes.
Apologies, I'm on holiday, and you might be able to hear the waves in the background.
The what?
The waves.
Okay. Oh,
Ocean.
okay. You're having
Ocean waves.
Lucky you, lucky you. Okay. I'm set.
Slightly warmer down here.
At what rate?
Sorry, what's that?
How warm is there?
It's 27 at the moment.
Good. Good for you. Okay. So let me share my screen, which I cannot see for some reason. Oh, no, I can. So, do we have to wait a little more?
No, we
Maybe.
can start right away.
Okay. So, hello,
I'll switch
everyone.
off if anything. If you need my assistance, just ping me. Okay.
Okay. Okay.
Thank you. All right. See you, everyone. See you next week.
Okay. Hello, everyone. So today we are dealing with equations. Please ignore this cap here. It's just that I used the same area as was for my lesson plan. But here are some equations which you haven't come across yet, I believe. We will talk through them and see some really useful tools and maybe just practice a little bit. Oh, just let me know, what is your usual way? Do you just listen to me or do you participate? Would you like to have some time before I start explaining the problem so you can think about it a little bit? You can just answer me in the chat. So no one is answering. Okay. Well, it's okay. In this case, I will just go through them and you may watch and see what I'm doing with them. So I like to start with the substitution method. It's very useful in all sorts of equations. So basically the most often what you see, the easiest one is to deal with quadratic equations. So we'll start with this one. It is sort of a quadratic equation. We cannot see it because we have power 4 for the x, but if we use our substitution method, we can substitute our x squared with another letter. Let's name t to be x squared. What do we get in this case? Well, we can rewrite our equation in this form. And now we have exactly a quadratic equation in terms of t. Just now, I have some message in the chat. Work through the problem, ask for contributions at different stages of the problem. Cool, great. I will just expect the same. So if you want to ask your questions or maybe you want to advise something, just let me know. By the way, before we go further, please let me know if you can see everything, if my writing is tolerable. And please don't hesitate to tell me if there are some problems. Okay, you can see everything. All right, cool. So from here, as we already see that this is a quadratic equation, we can just, well, usual stuff. By the way, maybe we can see something from here. Is it? Yeah, well, something special, some special. Perfect square. Yeah, correct. This is a perfect square. So how can I guess? Well, basically, I see a square here. Perfect square. I sort of ask myself, what if I look at the expression, which is 5t, right? Something which can be squared to 25t squared. Minus here, minus 2. So if I have this perfect square, if I open it again, I may see the middle one, which is 5. So conveniently in that. So this is the it's equal to 0 only if in the bracket. And that's how we get our answer in terms of t. You can leave it as 2/5. You can switch to decimals. It's up to you. I would recommend to stick to fractions, at least until you deal with this method, because chances are high that you will need to go. So let's come back to x squared. So now we know that my x squared is 2/5. So this is just a basic quadratic equation. We should always remember that we will get two answers in case we have such an expression. Well, we can have 0 here, and in this case, we get only 1. But the most common mistake is x is square root of 2/5, and that's it. No, that's not the case. It's always plus or minus. Cool. I don't think that's something, it's just a warm-up question. If you have any questions, just let me know. I'll hang here for a couple of seconds. But I can see that no questions are there. Cool. Let me erase this all. And now go to the next one. So the next one looks a little bit, yeah, there was a question. Yeah, you already, yeah, that's cool. So I would say that it should be x squared, right? X squared minus 6 over x. So yeah, let's look at this one. So first of all, let's sort of rewrite this particular term because it's not the same as this one, and we would expect it to be the same, but it's almost the same. So if we rewrite it, we would get x squared minus x squared minus 6 over x squared. Now I have plus 4, and here I have this, I put it to the same denominator, which is x, and this one x squared again, minus 6 minus 5 equals to 0. Yeah, and we can see it just right, that x squared minus 6 over x can be replaced by letter t. And in this case, we just get a simple, quite simple, seen often enough. Can you propose some ways of solving this one? Just, I do believe that by now you know different approaches. Yeah, factorize, I would stick to that too. So that would be what I expect, 5 and 1. And I have plus here, so the bigger number should be positive. The smaller number should be negative. And that's how I get it. Yeah, we can open it and check plus 5t, but minus 1, that's 4t, and plus 5 times minus 1 gives us minus 5. So that's how I get my answers. Remember, we always switch the sign. Well, That's just because we ask ourselves, when do we have this bracket equal to 0? Well, when t is equal to -5, and the same here. So now we can come back to what we had in hand. So this one is well, it's not tricky, it's just nasty looking. So we will have to deal with some rational equation, but we're not afraid of them. This bracket here, I do believe that you should be used to it by now, but just in case, I will remind you that means or, like not or when I take only this one or only this one, but this general or when I sort of have the unit of all solutions. So either t is equal to -5 or t is equal to 1, each case is valid. And that's why I use this bracket, just to somehow, maybe to simplify my writing, but it's up to discussion. Right, so what do I do here? Well, basically, when we are dealing with rational equations, it's better to send everything to one side, and that would be our left-hand side. So that would be x squared, and I switch 5 to the other side and switch its sign. So, and I also can already put it to the fraction, so that would be plus 5x and -6, correct? Please watch me. Sometimes I do mistakes. So if somebody's seen something, but I think it's fine. Yeah, I think it's fine. So that's my first one. And second one is x squared minus x minus 6 over x equal to 0. Now, well, we only can have a fraction equal to 0 if we have a numerator equal to 0, right? But for the denominator, and that's a very good habit, try not to forget about that. So the easiest way is just to forget all about that and stick to the numerator, and that's it. But well, basically, it may lead to some mistakes, especially if in the end you do not check your solutions like one by one. And in case of equations, that's what's helpful, but in case of inequalities, that will not help you at all. So once you try to sort of forget something in your mathematical solution, try to write it down. So if I'm forgetting my denominator, I'm sort of forgetting my limitations, and I have some, right? So from the beginning, I had such an expression which only allowed me to have non-zero access, right? Because it's in the denominator. So I sort of remember it. Here is my star. And after I've written it down, I will not forget about that. In case I will get a solution which is equal to 0, I will just get rid of it because it's invalid. But now I can go to solving, just my numerator part. And here we go to quadratic equations. And I bet some of you have already solved them. So that would be, for the first one, what would it be? Like, I think -6 and 1, right? And for the second one, it should be like 3 and -2, right? Please check my solution. It'll be fine if anybody just tell me, yeah, I got the same, or no, I got something different. Nobody's answering. Well, oh yeah, same answer. Oh, cool. Thank you so much. Thank you for your feedback. It's really helpful. Okay, that's pretty much it for solving, sort of simple equations, right? As long as you can go to quadratic equations, it's not that hard. So now let's move to solving some equations which have square roots. I will do it as follows. I will just take it out here and deal with it here. Yeah, that's much better. So let's look at those. Maybe I'll give you a couple of seconds to just, to digest what's written here. And maybe some of you will already propose something. Here's my chat. Yeah, just leave it somewhere here. Oh, I can leave it here to the left. Yeah, now I can see you all. Okay, any ideas? while you're thinking, I'll try to remind you that when we're dealing, again, with rational equations, as we've seen it, restrict domain of X so that expressions under radicals are non-negative. Yeah, well, that's what I was about to say. So first of all, when you're dealing with your radicals, always try with restricting your domain with limitations of your X value and so on. So the first step here is to write down the whole expression under the root, which is under the root, and to claim that this should be non-negative, right? So I do advise you to always start with this step, because sometimes you're so rushed, you will say, yeah, well, it means that X is bigger or equal to -1. That's obvious. That is obvious. But if you have a habit of starting with the expression itself, you may save some time, later when you are dealing with worse problems. Okay, so this is a limitation on the domain of the function. This is sort of what you get from this limitation, right? Here is the difference. But yes, still, this is just equivalent to each other, and that's where we started with. But what does it give it? What does it give to us? How can we deal with this equation? Here it is multiplication, right? We have a product of two functions. What can we say? Either, yeah, cool. So either this thing is 0 or that thing is 0, sort of, right? So if we have A times B equal to 0, that means either A is equal to 0 or B is equal to 0 in simpler words. But of course, as we have a special function here, we always would leave it only in the domain of this function, right? So we can ignore the -2. Yeah, everybody is already there. So two different possibilities. So either this one is 0, but at the same time we have this limitation, or we just have that this is 0, or square root of this is 0, which is just the same. So what will we get? From here, we'll get X is either 2 or -2, but as we have this limitation, this root doesn't apply to us. And here we get X equal to -1. Yeah, pretty much it. Okay, so now let's look at this, at second one. Maybe this was bad ringing it. Okay, so what do we have here? Again, we will start with limitations, but this time we will have, not only this radical limitation, but also something else. I'll start with my limitation on the function under the square root. This is it, and I'll rewrite it. Yeah, exactly. So we also have a limitation on this right-hand side. Why? Well, because it's equal to a square root. If a number is equal to a square root, this number should not be negative, right? So that's where I get my other limitation, which is X is non-negative. So altogether, we can rewrite it as X is squeezed in between 0 and 2. Both ends are there. So now what do we do? Now we do just simple thing. We just square both sides, and that's it. So we'll get this to the left, that to the right. We will rearrange it so we have a proper quadratic equation, and we can see it can be factorized quite easily. That would be +2 and -1, as again we have plus here, so this number which has bigger absolute value should be positive. And here we go. So either we have -2 or 1, but only one of those roots are valid, as we have these limitations. So we cancel this one, and we're only left with the final one. Please, in your solutions, always finish with the final thing, right? So the tutor shouldn't guess what you meant by that. You can also add something like answer, or you can just box it, anything. Okay. Well, number 3 then, pretty much the same. And I just wonder where should maybe I should again just take a snapshot and maybe put it somewhere here. Yeah, that would be our third problem. Again, where do we start? Well, just the same. We have some limitations here. We have some limitations here. And this one would be a little bit tricky this time. And we'll have to remember some inequalities here as well. So what do we have? Oh, yeah, somebody is so speedy, they already got an answer. But let's do it step by step just for everybody else's benefit. Okay, so first step, this should be non-negative. What does it mean? Well, let's try and factorize it, probably, or just, you can look at it as what are my roots of this expression, right? We have a quadratic function, sort of. Well, not sort of, it is a quadratic function in my left-hand side. So what are my roots? I've been said that it's -2 1/3. Let's just check on them. Remember Vieta theorem. So the product is -2/3, which is correct. Their sum is -6 + 1/3, which is -5/3, which is still correct. Yeah, I agree. Those are the roots. So it's concave up, and it's bigger than 0 or equal to it if we're looking at this particular interval. So that would be x less or equal to -2, or it's greater or equal to 1/3. Both are okay. But also we have this limitation, which is again 3x - 1 should be greater or equal to 0, should be non-negative, because it is equal to a square root. So in this case, we get just x is bigger than 1/3, and that means we are only left altogether, we're only left with this limitation, right? Because we need this and this to be, to be there simultaneously, right? So here we had two opportunities, but this one kills one of those opportunities. So we're only left with x, which is greater or equal to 1/3. So now what do? We just squared again. So here, lucky enough, we get just some quadratic expression. Here we get x squared -6x + 1, right? And let's rewrite it. So that would be 6x squared - 11x and, well, +3, right? It's sort of, I'm trying to send it to the right-hand side, but also rewriting it at once. So it's a little bit, I'm sorry, maybe it's a bit confusing, but I do believe you can follow it. So yeah, I think that's what we have here. Now we need to figure out the roots. I will just stick to old, good discriminant formula. And there is nothing to factor out, so I will have to actually calculate it, which I hate, but yeah, 12 times 6, 72, right? 121 minus 72 is equal to, let's see, 51 minus, oh, not bad, not bad. Okay, and always, don't stop here, always write down the square root of d, because what happens often, and I believe you've come across such a problem, you put this in the root formula rather than the square root. So never stop here, always sort of write a comma and write down the square root of d. So yeah, what do we have now? We have -5 plus or -7/6. That will lead us to either -2 or 1/3, right? Yeah. That's pretty much it. We need to look at what we have now. We have these limitations, so only this root stays. Cool. Okay, maybe just a few seconds for you to keep up, to write down, to digest, to ask some questions. Let me just come back. Yeah, I know it's a little bit tricky because I'm moving my screen. It's not that you can write down something when I'm moving it. You can always stop me, and I'm not erasing anything at all. So I can always come back. Are we ready to move to number 4? Why is it -5? Why is it -5? Where is it -5? Oh, here in the formula. A and B in the quadratic. Then I used the wrong. Okay, let us see. So this one is A, this one is B, this one is Oh, yeah, correct. Sorry, I looked at this. Oh, thank you so much. Yeah, you're right. I just looked at a different equation. Yeah, thanks. And I was a little bit bewildered because I got the same roots, and I was like, how did that happen? Well, maybe it's just yeah, exactly. I just used a different equation. Yeah, so it's 11 plus minus 7 over 12, right? So that would be 18 over 12, which is 3 over 2, and 4 over 12, which is 1/3. And that means that both are valid, right? Because 3 over 2 is also, yeah. Thank you so much. Yeah, thanks everybody who noticed it. Cool, yeah. I just watched one line up. Okay, I think now it's good. Tell me if it's not. There's no lag in Zoom. And okay, so now we move to this one. Oh, that's very, so to say, not traditional, but you see it a lot. So what's happening here? You're trying to substitute, but you're trying to grab inside this substitution as much as possible. So I will start with the whole square root, which would be t. And I noticed that that means that this stuff is 1 over t. Quite popular equation, or quite a popular one. I mean, like a structure of it. So what do I get then? I get t plus 3 over t. That's my 3 coming to the numerator, equal to 4. I'm an advocate for not multiplying both sides or not dividing both sides. Equation inequality got you from by something which is consisting of a variable inside. So we can multiply it by some number, but please never multiply it by t or any other expression which is with the variable inside, because sometimes, well, usually it changes the whole picture. You should always watch what's happening with your equation and see if you've missed or if you gain some extra solutions because of that. And as for the inequalities, oh, that would be a disaster because you totally change the whole picture with those what are the intervals of your variables which are you considering. So what I do instead of that, I sort of do the same, but I just keep my t in my denominator. So I just readjust it to the fractions, everything. So that would be t squared. This one would be sent here, that would be minus 40. And that would be plus 3, and that's my 0. So again, here I write down that t is not equal to 0. I'm not gaining an extra solution, or, even don't consider such a possibility. And I also have my numerator equal to 0. Of course, you can see that you will not have 0. Just in case, that's just a good habit. If you stick to it, you will not get into trouble later if you have, a worse problem. Okay, so what do we have here? Oh, that's the easy one. So that would be minus 3 and minus 1, right? And that leads to 3 and 1. And now we can substitute it back and also use the fact root equal to some good number, so we can just square both sides. So that would lead us to 3 minus x over 2 plus x equal to 9. Or 3 minus x over 2 plus x equal to 1. And now, well, as I just said, I do not like multiplying both sides, but if you have a rule, you can sometimes break it. So that's what I'll do here, just because it's a linear one, and just because I already, oh no, I don't have it actually, but I should have it. So here as well, we should have written down that x is not equal to minus 2 and x is not equal to 3, because those are limitations of my fractions. And also I should have said that this both these expressions under the radical are bigger or equal to 0. But as we can see, actually we gain those numbers which are good enough. Like this expression is equal either to 3 or 1. Both are non-negative. And also until that time, yeah, until that time, probably, I remembered this information about my denominators. Now, that's where I'll put it. I'll put it here. I remember about this limitation, but now that I remember about that, I just forget about my denominator. I multiply it. Just as I said, you know, there are some certain rules, but sometimes you may break them if you are very confident. Here, I'm quite confident that I'm okay with a linear equation, but, you know, just be aware of this possibility to make a mistake somewhere here. Okay, what do we have here? 9, 10 plus 18 to the side. Please check what I'm doing here because I'm doing it in my mind and I might sleep. So yeah, I have 2x, which is equal to 1. So x is 1. X is minus 3 over 2. Both roots are not in conflict with my limitation, right? So I think that's pretty much it. So again, wasn't I so obsessed with the domain limitation? Well, because as I saw as my solving, as we can see from my solving, I just got some special, oh, sorry, here they go. I just got my numbers and I just saw that they're good enough. I mean, my square root is equal to 3 and 1. There is no problem there, right? It's not a function or something. Okay, so I think that's pretty much radicals for now. Oh, no, because we have problem 3, right? Problem 3 is a special case, completely different from what we've done so far, but you've seen it in your, oops, later. Yeah, here we go. You've seen it in your assignment. So functions being continuously increasing or decreasing. So that's a useful trick, actually. You may use it with different functions, not only those, not only with radicals. It just depends on the function you're dealing with. Sometimes with logarithms, it can be useful. Sometimes with exponential functions, it's still with exponential functions, you know, that is a good case. Sometimes you will come across them. So what do we do here? Well, first of all, we may notice that this function is continuously increasing. Why is that? Well, the fact that it is continuously increasing, basically it's the fact that we haven't proven, but we sort of expect it because, you know, it's a good algebraical function. You deal with it a lot. It's sort of expected to be continuous. So like every dot is there. Why is that increasing? Well, this one is simpler. And we know that the bigger x is, the bigger square root of x is. And that means it's increasing. As long as we go to the right along the x-axis, our function is increasing, right? So that's what's happening here. And the same is happening here. On the other hand, the right-hand side is a function which is decreasing because of this negative x here, right? So this function, if I sketch it somehow, pretty much like, you know, pretty lame, it would be behaving something like this. The bigger my, oh, sorry, it's even worse. It's even worse because it's basically x is other way around, right? We cannot have x which is bigger than 1. So we will start with yeah, so it's a little trickier than that, but let me try to write it down like this. Yeah, it's a bit trickier. I wanted to draw a diagram, but I can see that diagram is sort of, well, it works, it still works. So this diagram's something like this, right? Something like this. So we can see that this one, it's sliding down, so it's decreasing. And this is a helpful trick. Once you have I'm sorry, something weird with my pencil. Once you have some area and you're having one function which is increasing and another function which is decreasing continuously, right? They can only intersect once. Because if we go to the left of this point, this function is already less than this, and this function is already bigger than this value, right? And the same here, but the other way around. So that means we're sort of guessing what is the one solution here, and we're quite content with that because we know it's the unique one. So if we have one solution, that is a solution. So now we need only look at this particular example. I do hope that I wrote it because I don't have my drafts with me, unfortunately. I was compiling those questions and I left it somewhere. So I believe what it was something like, what was my number here? If you have an answer, please write it down. I'm trying to remember. What would it be? X minus 5. Oh, really? Yeah. Cool. Thank you. Yeah, that's what happened. First of all, I compiled problem. And second of all, I've compiled a problem where the domains do not overlap. Thank you. Yeah, that's the problem. That's why I cannot guess my solution, because basically I just took it out of my head without any consideration other than the domain. Yeah, sorry, that didn't work as perfectly as I intended it to work out. That's because I don't have my draft with me. So yeah, the idea of this one was to show you that sometimes you can start with the domains only. Yeah, sometimes when you have an equation, it's dead end already, because if you write down the limitations, you will see just don't overlap, because sorry, this one is bigger. So your x is bigger than 5. It's also bigger than 2, which is, which is included here. But at the same time, it's less than 1 or equal. And that means that those domains do not overlap. So this one is coming this way, and those two are coming this way. And that means you don't have any solution at all. Why would the algebra still give there is not graphical solutions? I'm sorry, I don't get this question. What do you mean by that? Still give you solution with the not graphical solution? If you plot your functions, like here, you see here we don't have any solutions, and algebra shows us just the same. So I don't quite get this question about why algebra still gives us solution with complex solutions. Oh, yeah, it can happen if we're dealing with a quadratic equation. It can happen with with the roots as well, sort of. If you put it inside complex numbers, that will work. That will not work for real numbers. I can like when you sometimes solve equations and you get solutions that aren't valid. I mean, if you solve an equation and you get solutions and you tick them back and they're not valid, that just means that along your way, along your solution, you just didn't write down some limitations which were there. That's the only thing. So once you square something and forget about the limitations, once you get rid of a denominator and forget about its limitation, etc., with logarithms a lot, just be very, very aware of all the limitations you have with logarithms. So that's what's happening. And basically, I'm an advocate of writing down all the domain restrictions, all the restrictions, before you start doing your problem. And that's basically what I wanted to introduce you here, but I forgot what was my idea behind this problem. So that's why I thought it's mainly about the increasing and decreasing, but increasing and decreasing about point B. And now that I guess we figured out what was the problem with A, we didn't have any solutions. I will repeat it for those who will be watching this video and maybe a bit confused with what's going on. So this one doesn't have any solutions because of this domain issue. They're not overlapping. The B one is where my speech was planned for. So the B one is the case when this one is increasing, this one is increasing, that one is decreasing because of this minus in front of x. And here we can sort of guess it. And how do you guess? Well, you have 56 x and sort of, well, you try to expect a perfect square here, because if not, you're a little bit obviously the answer would be at least an integer number, right? So here I would expect it to be 16, right? So that would be x equal to 4, right? To get 16, my x should be equal to 4. And now I put it here, and I see some trouble because I think there was a misprint. Yeah, that's 11. One is square root of 9 plus square root of 1 equals to square root of 16, which is 3 plus 1 equals to 4. That was 11. So, okay. Is one in one of the previous questions, quadratic times the irrational functions. Why did we ignore some of the answers of the quadratic part? Because even if under the root it's negative, when you multiply by 0, it should be still 0. The problem is, that's a very good question. Thank you so much. So the problem is that if you're dealing with some sort of a function, and certainly here you've dealt with some function which was represented as a multiplication of two other functions, sort of when you start dealing with them, you cannot substitute, what did we reduce? -2. You cannot substitute it here, get a negative number and say, well, it's all right because I have 0 here. Because at the moment you put it here, at the moment you get your expression looking like this, have an invalid expression. You sort of cannot say anything about that because it is invalid. So while real numbers, you get such an expression, it's always it with multiplying it. Well, obviously multiplying anything by 0 will give you 0 in general sense, but in sense of dealing with functions, we even do not go there, okay? So important. Good. Okay, oh, sorry. No, maybe you didn't notice anything, but I had a lag here. Okay, that was problem 3. Let's go back and see what's my problem 4. Exponential functions, exponential equations. Well, let's split it. It's split it naturally. We'll just use the same thing here. Okay. So what do we do when we're dealing with exponential functions? Basically, we just need to remember that once we have power equal to a to the power of the restrictions, that just means that those powers are equal, right? So here we need to rewrite the right-hand side in terms of 7 to the power of something. And that is quite easy because 1 is always anything to the power of 0. And that's how I get 7 to the power of 3x plus 2 equals to 7 to the power of 0. Once I have it, I can get rid of my... Oh, sorry, a little bit not there. And just consider my function. Did you solve the problem 3b by inspection, or was there a method? Just, yeah, you know, I was looking at it. I was trying to research what would be an appropriate. So the hint here is, as I said, if you sort of trying to solve it using this approach of increasing and decreasing on the different sides of your equation, you sort of guessing for the solution, right? You're expecting it to be the unique solution, so you try to guess this one. And if you have such a problem, usually that means that they would expect you to find some integer, at least integer, but usually a natural number. I would say integer is better. Yeah, so that's what I did here. I was looking at my right-hand side. I was thinking like x minus 10x should be a perfect square. And I was sort of counting in my head. It shouldn't be, it could have been 36. But I decided that I'll check 16 first, and that worked. Okay, Okay, sorry. Now let's go back to exponential functions. Okay, so here again, we're only having, oh, that would be minus. We're having quadratization. That would be x minus 2 times x minus 1 equals to 0. Oh, sorry, my solutions. No limitation here. Nothing at all, because we're dealing with 7 in the base and just some. Now let's go to point B. This one is a good one. That's a substitution method again, because we can see we have something squared compared to this one. Oh, and this one is times, but it's just a confusion here, because in English math, it's always a cross. In some other cultures, it's a dot. So yeah, sometimes I mislip. Okay, so what do we have here? That's 4 to the power of x equals to t. You may use any other letter you like. I'm just used to t, like temporary. And that's my t squared minus 3t minus 4 equals to 0. And here we go. That should be negative. And that one is positive. And my t is equal to 4, or my t is equal to minus 1. And that's a good one. So as I said, for exponential equations, usually you don't have to start with those limitations, because, well, sort of, we don't have any limitations yet, but we will see something now. So what's going on? We're having 4 to the power of x equal to 4, or 4 to the power of x equal to minus 1. I never limit my t here, because that's where I could have said, well, if I have such a, my t is negative, because when I come back, that this one is nonsense, right? And I can just cancel it right away. So it's up to you. You can be quite meticulous about that, but you can just do it as I did it now. And the only thing I'm left with, and I'll do it properly, so 4 to the power of x is equal to 4 to the power of 1, and that's how I get my x is equal to 1. That's pretty much it. Yeah, pretty much it. So yeah, the tricky part was that one of the solutions didn't work. Okay, that was problem 4, right? Let's see what we have and how many times. Oh, okay, let's just, yeah, some other problems to consider, to practice. After that, we'll go to logarithms, and if we have time, we will look at some problems with parameter. Okay, what about here? So one of the tricks for this one, and we've seen it today, and I said it's quite an often structure. So what would I do here? First of all, I would get rid of numbers in my power. I will just stick to the variable. How can I do it? Well, basically using the rule that if I have a sum in my power, I can split it like this, right? So that would lead me to 4 times 2 to the power of x. And close enough, that would be something like this. Again, 4 times 2 to the power of minus x. That's what I'm doing here. That's my C. Why do I do that? Because now I can totally substitute. My temporary variable would be 2 to the power of x. That means that 2 to the power of minus x is just 1 over t, right? And that's, again, that comes to the fact that a to the power of minus 1 is just 1 over a, right? So 2 to the power of minus x is the same as 1 over 2 to the power of x. If that's not clear, please let me know. We will look at it closer, but I believe it's just, you know, some usual stuff you already know. So, okay, what do I do now? I have 4t minus 4 over t, that's obtained from here, equals to 15. And again, I just use my fraction form, so that would be 4t squared now minus 15t plus Oh, sorry, that's not minus. That's minus 4, right? Equals to 0. Again, t is not equal to 0, but that's actually, I shouldn't be bothered about that because I know that my t is an exponential function. It shouldn't be equal to 0, but just as I have it as a habit, I would still write it down. And 4t squared minus 15t minus 4 equals to 0. Can I do it some way other than just look at the discriminant? I guess not. So that's what I'm left with. That would be 64, right? 16 times 4, 64, right? And yeah, that's good. That's good because square root of d is 17. I do hope that you know all the perfect squares up to 20 at least. It's better to know them up to 25. Quite convenient. So what I have here, come back to the same equation, 15 plus minus 17 over 8. And the two solutions, which are 32 over 8, which is 4, and minus 1/4, right? Yeah. Now we come back to our x variable, and we forget everything about 2 to the power of minus x because that card played itself. So now we go to 2 to the power of x, which is either equal to 4, or again, we get something like that, which is not working. So we just don't go there. This is a dead end. And here we have just 2 to the power of x equals to 2 to the power of 2. And that's how I get that x is equal to 2. That's it. That's it. Okay, now about those two. Those are a little bit tricky. They are, well, let's look at them and see what's in there. Okay, so I'm just a little bit worried about number D. Maybe that's not what I was planning to. Okay, let's see. Let's see how it works. Where is it? Okay, we'll see. So what's going on here? Well, we have different bases, right? This is something like 2 to the power of something. This is 3 to the power of something. But this one is both of them together. So let's see what's going on here. Let's just use different, different substitutions probably. So what do we have? We have 2 to the power of, let me see, do I need 2? So what do I basically have here? That would be my 3 to the power of 3, I mean 27. That would be 9 times 4. So maybe I should use the substitution for 3 and 4 instead of 3 and 2. So if it is 4, that would look like 4 to the power of 3x is equal to 2 times, that's again times, 3 to the power of 3x minus 3 to the power of 2x times 4 to the power of x. Now, just let me know if you follow me, how I got it, but pretty much it was something like that. So I sort of added x to each power. So what do we have here? Well, let's try and use t, which is 4 to the power of x, and for example, q, which is 3 to the power of x. And what do we get? We get t cubed to q cubed minus t q squared, right? Right. So let us see what's up here. So it's something like that. Minus 2q cubed equal to 0. Let's maybe split this one. Yeah, I see where it goes. Oh, that's a funny one. So that one minus q cubed minus q cubed equals to 0. And that's what I'll do. I will group those two and those two. And if I group them like this, what do I get? Here it's quite obvious. I just factor out q squared and I get 2 minus q. And that's a lot because I do expect to get the same here, right? Because that's the formula of the difference of two cubes. So that would be t minus q, t squared plus tq plus q squared. I do hope you remember this formula. In case you don't, usually it will come like, usually we'll have two different formulas, like sum of two cubes and difference of two cubes. But I do want you to revise you in case you do not sort of recognize it here. But in general, what would you expect? You would expect the same sign as you had here in the first bracket. So let me just write it down for you. So that would be a plus if you have plus here, or minus if you have minus here. And then the second bracket, that's other way around. So you only have one minus. So if you already have it here, you don't have it here. But if you had plus in the first bracket, you will have minus in the second one. Oh, sorry, that's A. Yeah. AB plus B squared. This is very close to a perfect square, right? If we had two here, that would be a perfect square. That's why usually it's called imperfect square. So that's not a complete square, right? So, okay, let's come back to that. That's q squared t minus q. And that's good because now we can factor out these brackets, this factor t minus q, and we're left with t squared plus tq plus q squared minus q. Is it plus or minus? It's plus, right? No, it should be just a sec. Q squared. No, it's plus. What a shame. I wanted them to factor out. Oh well, it's still, we still can solve it. It's just a little bit trickier. Okay, so what do we have here? We have the product of two different mathematical expressions. First one is quite obvious. If t minus q is equal to 0, if t is equal to q, then that's one of the solutions. And if we come back, that will leave us with 4 to the power of x equal to 3 to the power of x. And that's an interesting one. Well, basically at this point, you can just say that is only possible if x is equal to 0. That is not sort of, you don't prove it. You don't prove that there is only one solution. We can, though. Let me show you how let me show you how to prove it, but I don't think that you have to do it in your assignment. You can just, from here, you can just say, well, x is equal to 0, and that's it. That's the only possible solution. But why is that? Why is it the unique one? Because if I divide each side by 3 to the power of x, I will obtain such a thing. And here, now, I can say, well, this is my function with the base, my exponential function, with the base which is bigger than 1. So it's continuously increasing. And while it's continuously increasing, it can only be 1 once. And that is when my x is equal to 0. If we're being very precise, that is the best way to express it. If we're sort of, being not so meticulous, we can just say, well, from here, this is the only option. And now let's come back to the second part, because that's the trickiest one, right? So we have t squared plus tq plus 2q squared, which is not looking very good, but this one is called a homogeneous equation. I'm not sure if you had it with us, but homogeneous, that means that altogether we have two letters here, t to the power of 2, 2 letters here, and 2 letters here. That's the only thing you should know about homogeneous. But why I even use this word here is that once you see them, you can use this following trick. Let us pick up for example, this term, and let us divide everything by q squared. As long as t and q are substitutions of exponential functions, I don't have to deal with them being equal to 0. So when I do that, and that only works for homogeneous equations, that's why I use this term. As I do it, I get something like this, right? So it's t over q squared, because that was q squared. Here, 1q is factored out, but 1 remains. And here I'm just left with 2. So what's happening? Well, sort of, I'm having another quadratic equation. You may use a third letter here. And yeah, I know it's a little bit frustrating that we're using a substitution method for a substitution method, but that's what happens when we're dealing with real mathematical problems. So you may just use it for your benefit, just to make it look easier. Other than that, you don't have to do that. And well, what I'll do here is try to solve it, right? So that would be my discriminant, which is, surprise, surprise, it's negative. And that means I don't have any solutions. And that means that here again, I don't get any solutions. And that's fine. That means that the only solution I got is here. We just had to sort of check this particular case as well. That's what's happening sometimes. Okay, so that was a good problem, because what we had here, we had double substitution. We factorized our expression. We had to deal with the homogeneous expression. So 3, 4, maybe, yeah, I didn't count, sorry. A few useful tools, a few useful ideas for you. So quite a good one. Okay, and now let's go to this one. This one is easy. A bit easier, at least. It's not about some homogeneous freaking equations. It's about, well, it's about exponential functions, and I'm sorry for the quality of this, but it's the best I can manage. So that's about 2 to the power of something. Let's see what's happening here. First of all, let me rewrite everything, every term, in terms of 2 to the power of something. This one stays. This one, oops, why I tend to change those signs? Okay, this one goes to doubling. Remember this is a useful one. So if you have something to the power of n and then to the power of m, you sort of multiply those powers, right? That's what I'm implying here. So that would be 2 to the power of 2 times 6x minus 1. So that's 12x minus 2, plus doing the same, but now it's 3 times. Let me write it as 12 also. 12x minus 3, right? And minus 2, again, 12x minus 4 equals to 1280. Okay, what do I do with that? Well, you may say that you can substitute it. You may. It's just that, let me advise you a simpler idea here, okay? So let's look at it. What is the smaller power among those? Which one is the smallest one? And you can answer me in the chat box. Oh, yeah, I have a new message. Is it the small one? 12x minus 1. Is it a smaller one? No, of course. 12x minus 4 is the smallest. Yes, of course. And let me just factor it out. I'll factor out this term. What do I have? Yeah, all of you has answered to me. Yeah, oh, yes. Okay, so what do? I factor it out, and I see what's going on? What's going on? There is a joke about teachers when they have something in their mind, they write down something different and they mean a third thing at all. Okay, so that was my factor. Now what's left? This one is 3 steps bigger. So that would be 2 to the power of 3. That's what's left here, right? Just this one is a tricky one. So I'm sort of trying to take away 12x minus 4 out of 12x minus 1. So maybe to make it a bit more evident, I would just do it like this. So I subtract it, right? So when I take out some powers, I subtract them, and that's -1 minus -4, which is 3, right? Because 12x is just dying. Yeah, similarly, here I get 2 to the power of 2. Here I get just 2. And here I get 1. Never forget that the structure in the brackets, once you factor something out, the structure in the brackets should be the same as the structure in the original expression. So if you had 4 terms, you will still have 4 terms. I only mention it because sometimes when you factor it out, you sort of think something, I believe it's something like, I'm left with nothing, which is actually 1, but you think that it is 0 and just don't write it at all. I've come across many such mistakes, so I just want to stress it here. So yeah, that's what happened. And now I see that this is just a number. I can figure it out. Can you just tell me what is this? What's left in my brackets? What would it be? Yep, it's 5. Yeah, cool. And now I can divide my right-hand side by 5. That would give me 256, correct? Yeah, if I divide it by 5, it's sort of doubling the first 3 digits. And why did you change the exponent to 12? I don't know. I don't know. It's just me. Sorry, I had a long day. A lot of lessons today. No, it was unintentional. Okay, yeah, so that would be 2 to the power 12x minus 4 equal to 2 to the power of 8. Yeah, and that's it. We just are left with the linear equation. And a nice one, right? So x is just equal to 1. That's it. But this one is a good trick. So it's not, not always it is necessary to substitute something. It may be easier for you, but sometimes if you're confident enough, you can just use it as it is. Okay? Okay. So what are we doing now? Oh, we finished this one and we can move to how many times? Oh, okay. We can move to logarithms. Yeah, that's great. That's great. Maybe just let's look at it because the problem five is actually a simple one. I was just trying to prepare some problems for revising what is a logarithm, but if you're good enough that if you're, confident enough, we can skip it. So basically what I wanted us to remember is, well, the definition basically. So if we are dealing with such an expression, that only means that if I take a to the power of this, I will always get b. And also some limitations. So a is always positive and not equal to 1 because it's, we're dealing with 1 to the power of something. It's always 1, and also because it doesn't give us anything, any profit. And b is always non-negative. Oh, sorry, it's always positive. Yeah, so those are my limitations on a and b can be some functions and some expressions. So I think we should skip this one for now. That's just some practice. And maybe problem 6 as well, because they do not relate to equations themselves. They're just to warm up, but we don't have enough time. So let's go straight to these particular problems. Let's start doing them here. And in case we need some space, I will just screenshot it somewhere. So what's going on here? What can we do about it here? I'm waiting for your proposals. Any ideas? So we're dealing with this one. Change 1 to, yeah, that's a good start. So let's rewrite 1 as log 6 minus log 6, 3. Combine those. Yep. If we combine those, what do we get? We get log base 6, and here 6 over 3. About restricting the domain, just hold there. I'll come back to that. Yeah, so what we get here is 6 divided by 3, because that's the rule of the restricting domain. That's a good one. And that's where I will start with, and I'll start with this here, for example. But for this one, just because to the right we have only number, we don't have any variables here. Now, because as you will see, we will not come over our our domain, sort of. So when we have it like this, we can only say that as exponential functions, if the base is the same, we only are left with the fact that x is equal to 2. So we don't need this restriction here. It's just an easier example, okay? But you should always remember it. So once you should always be careful enough, write down just in case. Okay, let's go to the next one. So it's B. Maybe I'll just move it from here because I will need some space for that. Okay. So, well, basically, no, this one is easier. Yeah, this one is easy enough. We don't have to deal with the domain here. Let me show you why. Well, just the same as we do with the exponential function. And we will be left with x squared minus 3x equal to logarithm base is 2. What do I put here? Yeah, 4. I put 4 here, and that's it. I don't have any restrictions because basically the only possibility is for this function be equal to 4, and it is already inside my domain, right? So I don't have to write it down. And that's it. That's the only thing I'm left with. Will you excuse me if I just stop here? Oh, yeah, it has to be greater than 0, but it is greater than 0 because it's equal to 4, because that's how the equation is designed. We rewrite the right-hand side, and we can see that from here, x squared minus 3x is 4, which, it exactly satisfies our restrictions. Okay, so that's why I don't minus 1. Oh, you're right. No, you're not. So what? Minus 1 is okay. Let me check. Okay. Minus 1. Yeah, it doesn't bother me. Even if minus 1 is a solution, that would give me here plus 3. So it still is. So don't worry about negative numbers. You should worry about the expression itself. Okay? So once you have, just let me be clear, you can write it down, but once you have that this particular expression is exactly equal to 4, you don't have to bother about that anymore. But in case you don't feel, I myself sometimes write down redundant restrictions just in case, because I know that sometimes I sleep. So yeah, you can do just the same. It's just that here it was not so necessary because we just reduced it to one particular case. Yeah. Okay, so I think now it's clear. Now let's go to this one. Yeah, what I wanted to ask you, let me stop here. I will not solve this equation because it's easy enough for you to deal with that. We will just stop where at a stage where we get to some equation which is really easy, a quadratic one, for example. So here, again, substitution method works just fine. So I will just substitute t as a logarithm x to the power of 2. I will not deal with my restrictions by now, so I'll just solve this one. And here we go. After that, I will get my solutions, which are 3 and 1, I believe, right? And again, as I have my logarithm to be equal to some exact number, I don't care about my restrictions because I will not get outside my range, okay, outside my domain. So that would be my answers. That's it. So that's how I deal with that. So this one is a basic logarithm equation, right? So I got it. X is equal to, yeah, thanks. I don't know what's going on. Maybe it's just I'm that tired. Yeah, thanks. X is equal to 8, of course, because it's 2 to the power of 3 and not 3 to the power of 2. Yeah. Okay, now let's go to point D. Okay. What would you propose? Yeah, that's a good one where we can have all this stuff with restrictions and everything. What would you propose for D? Where do we start with? Yeah, well, that's a good, somebody proposed to combine those logarithms. That's a good one, but that would be our next step. Here, and that is very important, here we'll start with writing down the restrictions. Why is that? Because after we combine two logarithms, we actually change it. You will see. So first of all, let me write it down. So x is bigger than 0, x minus 2 is bigger than 0, and 2x minus 3 is bigger than 0. Now, being that said, well, I can rewrite it if you wish. I can do it straight away. So that would be x bigger than 3/2, and also I can sort of limit it to 1. So the biggest one is x bigger than 2. So that would be the final one. Yeah, and now what do? Now I try to combine them, and that's where I show you that this one is changing a little bit, changing the whole picture. To x minus 3. Yeah, so if I combine them, I just have log base 3 x times x minus 2, right? If I wouldn't start with my restrictions, if I would come to them only at this point, I will have a different picture, right? Because I will have this product to be positive, which actually can be split into two different cases. Both are positive or both are negative. And from here, I know that I'm only allowed to have both positive. So that's why I start with this. And only after I've written down all the restrictions, I proceed with the solution. Okay? That is very important for this particular case. That's a good example of where it works weirdly if we do it other way around. But from here, and with those restrictions, which we already have, we can just take away our logarithms. That would lead us to x squared minus 2x, left-hand side, equals to 2x minus 3. And this particular limitation, I can write it down like this. So this bracket means and, like I have to have this and this simultaneously. And we're only left with the equation and the limitation. So I will not solve this equation, though it's obvious. I will just leave it as this. So you have two solutions, and you only leave the one which satisfies this limitation, right? Okay. Okay. And the last one, which is not, it's not hard one. It's just maybe a funny looking one. Okay. Yeah, what do we have here? Once again, we'll start with the limitations. Second of all, we'll rewrite the right-hand side. What is this? This base is 5. Yeah, it's just 3. Yeah, absolutely. So this one is 3. Those two can be combined now that I have my restrictions here. So that would be log 3 of x plus 2, 5x plus 4 equal to 3. And the only thing I will need to do is to rewrite the right-hand side, sorry. That was 3, so that would be log base 3. And what would be here? What should I place here? 9. 9 is not enough. 27, yeah, 27. That's my power. Yeah, so that's what I get if I take 3 to the power of 3. No, that's fine, that's fine, that's fine. It's good when you make mistakes, actually. I mean, first of all, you learn through them. Second of all, you make me stop and discuss it, and that's really helpful for everybody because everybody does these mistakes. Look, I've done just the same one a few minutes ago. Yeah, and so we only are left with such an equation. And I do think that you can do it without me. Just once you get the solutions, you should check if they satisfy those limitations. You can work with those limitations as we did in a previous example, so sort of limited to one particular inequality, right? But it's up to you. You can just do it anyway. Okay, so that was our stuff with the logarithms, and let's maybe discuss problems with absolute values a little bit, because there are a few tricks I would like to show you. Some of them you may see in your assignment. So first of all, well, first one is just it was for some practice, honestly, nothing special here. So basically, when you have absolute value equations of this form, those are the simplest ones. So because that means that those functions, whatever expressions you have, are either equal or I call them minus equal, like opposite numbers. So that would be written like this, my or bracket, and another way. So for the first one, basically, and I will just rewrite it, we have two different options. First, we get such an equation, and we can easily just rewrite it as a simple quadratic equation and solve it. And second, I have just the same on my left-hand side, and I change the sign of my right-hand side. It can be other way around. For example, here you may rewrite it as minus f of x equals to j of x. It's, it depends on the problem. For example, if your function here is more convenient for being switched to a negative one, you can change this one or that one. It's up to you. So those are my two possibilities. You can also split them as first and second option, because maybe here it would be easier to solve one separately and second separately. We don't have any restrictions, so that's pretty much it. It's a little bit trickier, and I want to talk about it here a little bit. If we're dealing with such a case, let me just compile an example. Please don't look at the numbers. They're just out of my head, but I want to mention it. So what is the problem here? Basically, there is no such particular problem, but we may always consider what is it here, what is the function here, because as with square roots, it cannot be negative, right? So once we're dealing with such equations, we should always consider what is the function here and write down the limitation, the restriction on it, because as it is equal to some absolute value, it should be non-negative. That's the only thing I should mention here. Now, as for problem B, that's a good one because it can be solved both with the use of geometrical approach and also with the use of so-called interval method. So first of all, let's start with geometrical approach. And this one is, so if you have an absolute value of some number, this is, remember, this is the distance from our number A to 0 on a number line. So if you have some distance, for example, you know that your absolute value of something is 5, that means it's 5 steps to the right or 5 steps to the left from 0. So that would be exactly minus 5 and 5. And so from here, we can also say that if we have a difference, absolute value of a difference between two numbers, that is just the difference between those numbers on the number line. So this distance between those two numbers is absolute value of A minus B. So now we can sort of look at this problem as this is a distance between my unknown x and -2, I can rewrite it like this, and between my unknown x, just the same one, and 3, and it's equal to 5. So I can just draw a picture and say that this is -2, this is 3, and I need my x to be somewhere so that the sum of the distances is equal to 5. What if I put it here? And first of all, let's consider what's the difference between -2 and 3 altogether. What is it? Yeah, it's exactly 5. So if I put my number x somewhere outside this range, I can easily see that my distance to, for example, here, to 2 is bigger than 5 already, and I add up a distance to 3. So it doesn't work. And the same here. So what if I put it somewhere here? For example, I don't know, that would be -1. What would be my sum of my distances? Exactly 5, right? So that's exactly what I need. But if I move this point inside this range, every such point fits. That's a funny thing, because using this equation, we actually described a segment, an interval. So for this particular problem, the answer would be a segment, an interval -2, 3, both points are included, both ends are included. And that's a good one, actually, because, you know, it's not that you can often describe some set with just one simple equation. Well, obviously you can if you have many variables, but for one variable is pretty much amazing. Yeah, and the last thing, maybe the last thing I can mention today is a so-called interval method. This problem is too easy for this, but still this interval method is very, very helpful. So once you are dealing with absolute values, always keep it in mind. So what is it? Basically, it's pretty much the same. It's close to interval method, the one we use, or a table method. Sometimes you call it like this, the one we used with quadratic inequalities. What do we do? So we're looking at those absolute values separately, independently, and look at their sort of points where we change something. Yeah, changing points. So for this one, a changing point would be -2. What does it mean that it's a changing point? Well, basically, it means if we're bigger than -2, then this absolute value can be opened as it is. Yeah, if x is 5 or 0, then the value inside the modulus is positive, and we can just get rid of this absolute value altogether. And if we're sitting here, that would be a negative one. Remember, we had our this is a different curve bracket. Yeah, it's not the same as simultaneous. And I'm sorry about this notation. Math is not hard. It's just that the notation is confusing. So we have a if a is greater or equal to 0, and minus a if it's negative. So that would be our change point for this one, and that would be 3 would be our change point for this one. Now what I do, I'll rewrite this equation, getting rid of those moduluses altogether. How do I do it? So for this particular interval, both moduluses can be just skipped because this one is a positive number and this one is a positive number. So I can just rewrite it as x plus 2 plus x minus 3 equals to 5. And if I solve it, I will get 2x plus 1 equals to 5. And I get x equal to 2, right? What's the problem? I sort of got an answer. But the problem is that I got an answer which does not belong to the interval I was living in. So that's why I cancel it. It's not valid. 3, no. Oh, yeah. Oh, yeah. Sorry. But that was a good example because, you know, in case, okay, here it is minus, and that will give you some answer, but that's an important one. So once you get some answer, which is like an answer, but it's not here, that's why I was so stuck to this idea. So if this answer is not here, you cancel it. That's the main idea about interval methods. But here, yeah, unfortunately here, there was one answer, which is just 3. And that's a tricky one. You could have looked at this interval as the one including 3 or excluding 3. In case you're looking at it excluding 3, you would still cancel it. You will get it from a different interval, but it's just, just something to mention. So the second thing is this interval, and here, this one changes. That one stays the same. That would be x plus 2, but that's 3 minus x now, a negative one, an opposite one. And here they cancel each other, and we have 5 equals to 5, which actually means that it's valid for every x. Again, for every x from this particular interval, because we're living in it. We're only considering the solution in this particular one. And the last one, well, it should be opened like this. I inverse them all. And again, here we would, I believe that would be x equal to minus 2. It's, as I said, it's not a very good problem to use this method, but once you have many different absolute values summed up together with some coefficients probably, that is really, really helpful. You don't have to deal with the 2 to the power of n different ways. You just slice your number line in a few intervals and deal with each one separately. I think that's pretty much it. If you have any questions, please shoot. Any comments? I'm sorry for my mistakes today. Maybe it's also because it's very dark in this room and I'm sort of, thank you for your feedback and for your work. Any questions? Anything at all? If not, then just thank you. Don't hesitate to contact us in case you have any problems. That's it. Thank you. Thank you. Thank you so much for your kind words. Okay. Hope to see you soon. Bye.